So let's start then. So good afternoon. So today we will be starting with this frequency sampling method, which is also regarded as Fourier transform method without using the window. Okay. So herein what happens, if you see, we have this question: design a LPF with the following specifications. The cutoff frequency of the filter, it has been given as 500 Hertz. Sampling frequency, it has been given as 2000 Hertz. And order of the filter, capital N, it has been given as 10. Okay. So herein the alpha would be equals to 5. Okay. Now the first thing is that we need to find out the cutoff frequency in radians. So herein we are given the frequencies in hertz. So the cutoff frequency should be found out. Omega c is equal to 2 pi fc by fs. Okay. So which gives us a reading of pi by 2. Sorry, it should be pi by 4. Yeah. So pi by 2. Sorry. Hmm. 2 it gets cancelled. So it gets pi by 2, right? Now, the next step is, once we have found out the omega c, we have this determine the transfer function. So the transfer function is given by hk equals to 1, 0 to pi by 2 modulus of omega, right? So we have already discussed about this, and 0 for other frequency components. Now the gameplay, it changes. So when we are having this thing, so what we have, this cutoff frequencies, we discussed about the distribution of the frequency components. So it was 0 to omega c and 2 pi minus omega c to 2 pi, right? Here, what is omega c? Omega c is pi by 2. If you convert it, take it as say 3.14, pi as the 3.14 and divided by 2, we get 1.57. So this point is nothing but 1.57. Okay. Similarly, over here, omega dash c, if we consider this as omega dash c, so this is nothing but your 4.71, and our 2 pi is 6.28. Okay. So what happens? Our pass band, it would be in the region of 0 to 1.57 and 4.71 to 6.28. Okay. So if our values are within this range, frequency components will be taking those values, and if it is outside these two ranges, then we will be considering those as 0. Okay. Now here, our order of the filter, it has been given as 10. Alpha is 5. So capital L, it would be 10 plus 1, which is equal to 11. Okay. Now we have to sample this frequency response, okay, such that the whole frequency spectrum from 0 to 2 pi, what we will be having? We will be having 11 number of points. We should be having 11 number of points. Now how to do that? We do this by finding out a delta frequency component, or you can say delta omega or delta frequency component, which will be given by 2 pi by 11. Okay. So at what positions this point should be? this point should be at k delta positions. That means 2 pi k divided by n plus 1. Okay. Now, when the value of k is 0, then k delta would be 0. Okay, k delta would be 0. Then when k is 1, it is 0.57. When k is 2, 1.14, and so on, and we get to the point 11 where we are having 6.28, which is nothing but by our 2 pi. Okay. However, in the z plane, we have seen that 0 and 2 pi both are the same point. So since we are taking 0, we will not consider the last point. We will not consider the last point. Okay. So what we get, we see we will get 11 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We are getting 11 points. Okay. Now, which points we should be considering? We should be considering the points in the range of 0 to 1.57 and 4.71 to 6.28. So if you see 0, it is within this range. 0.57, it is within this range. 1.14, it is again in this range. So we have taken these points. When k is equal to 3, we get 1.71. Now this 1.71 over here, if you see, it falls in the stop band range and it continues up to k equals to 8. The values, they fall in the stop band range. Okay, the values falls in the stop band range. Then again 9 and 10, it falls within the pass band range. Okay, falls within the pass band range. So these are the positions of the frequency components or the sample frequency components that will be considered while we will be designing the filter. Okay, up to now it is clear. We drew the frequency response. From there we found out what are the omega c values, what are the pass bands, what are the stop bands. Now from there we try to find out at what frequency points we will be sampling, and we identified that point up to this mm, up to this point of the numerical. Okay. Now next is calculate h cap k, which is the sampled signal components. So it is given by e to the power minus j 2 pi divided by n plus 1 into alpha into k. Okay. So for h cap 0, the k value is 0, so we get 1. Okay. So if you want to simplify this, it basically becomes e to the power minus j 2 pi by 11 into 5 into k. Okay. So you can write it as e to the power minus j 10 pi by 11 into k. Okay. So this whole thing, it is in the in the superscript e to the power form. Okay. Now you change the value of 1, so we got this one. So you take the value of 1, so e to the power minus j 10 pi by 11. Then k equals to 2, it is within the range. We have to take h cap k h cap 2, it is equal to e to the power j 2 into 10 20 pi by 11. Okay, then 3 4 5 6 7 8, they are not there. Then we have 9 h cap 9, it is 90 pi by 11. And lastly, for the 10 one, we will be having e to the power minus j 100 pi by 11. Okay, so these, see, these values are the same thing. Okay, now we need to find out hn. We need to find out hn. So what is hn? Hn here, it is given as 1 by capital N plus 1 h cap 0 plus 2 of real component of this one, addition of k equals to 1 to L minus 1 by 2, that means 5, k equals to 1 to 5 h cap k e to the power j 2 pi kn divided by n plus 1. Okay, so it is what you get. If you come over here, h to the power 0, it is 1. Then we are having 1 and 2. So when we are having 1 and 2, h cap 1 is here multiplied by e to the power j pi n by 11, because k is equal to 1. Okay, then for k equals to 2, this one e to the power minus 20 pi by 11 multiplied by j. Since k is equal to 2, 2 multiplied by 2, 4 pi n by 11. Okay, you got my point. Then 4 and 5, for values 4 and 5, 3 4 and 5, the values are 0, so the values do not exist. Okay, so our this equation, it transforms into h of n of this equation. Okay, now if you solve this, so you get 1 by 11, 1 plus 2 of real of e to the power j 2 pi by 11 n minus 5 plus 2 real of e to the power j 4 pi by 11 n minus 5. Okay, so this becomes the theta. So if you break it down, you get 1 by 11 plus 2 by 11 cos of 2 pi by 11 n minus 5 plus 2 pi by 11 cos of 4 pi by 11 n minus 5. Why? Because we are only taking the real components. We are only considering the real components. So our h of n, for h of n, we get this equation. We get this equation, right? Now change the value of n. N will be varying from 0 to 10. So change the value of n and calculate the hn value. Okay. Any doubt anywhere? Which one? This one. Here, h cap k into e to the power, this thing h cap k, if you see the second one, e to the power minus j 10 pi by 11 multiplied by e to the power j 2 pi. What is the value of k we have taken initially? Here we have taken the value when k is equal to 1. So here it is 1. So you have pi n divided by 11. Okay, you see. Now if you say e to the power, see I have taken this negative inside. So if you are taking the negative inside and you are taking say j 2 pi by 11, okay, so you are taking this 2 common, so you get n minus 2 into 5. Okay, in the second case what will happen? For k equals to 2, for k equals to 2, what we have? We have 20, and this would become 2 multiplied by 2, 4. So here what we have taken? 4 common, e to the power j 4 pi by 11, again n minus 5. Okay, so this is in the form of e to the power j theta. So cos theta plus j sin theta, right? But we are given with real part, so we will only be taking the cos component. We will only be taking the cos component. So when we take this cos component, we get this thing, and just we are left with n values. Okay, now you fill in the values of n, and you will be able to get the hn components. Okay, so this is it. So after that, you know the procedure. You have to find out the transfer function, and once you find out the transfer function, then you have to realize it. And if I give you find out the amplitude response and phase response, you have to calculate. Okay, चलो करो solve it.